I'd like to thank the organizers for the opportunity to present my work, giving me the opportunity to present my work. So I'll talk about these hydro simulations we are running since the last year, and briefly about the light synthesis process and our results. This is done with the supervision of Professor Raghunath Srianand and with collaboration of Nishikant Khandai, Professor Nishikant from Niger, and Professor Prakash Gaikwad from IIT Indore. And these simulations are aimed at producing the first set of galaxies in cosmic dawn. And there are some big questions in this period which people are asking. And we want to explore whether the conditions under which these galaxies formed and evolved and affected their environment, is it similar to the present local universe or is it different? And since now we have observational data from ZWST, we can compare the results, and if needed we can improve our understanding. Now what ZWST observes is, you can observe the spectrum, which is a little bit expensive, or you can observe the photometry points and you can fit a spectrum. Now what you observe is the UV to optical band in the rest frame, and there are various spectral features from which you can infer a lot about the source and its environment. What I will focus on is the UV luminosity, which is how bright the source is at 1500 angstrom. And this actually tells about the instantaneous star formation rate over the galactic time scale. And for local universe, there is actually very well calibrated relation which tells you star formation rate given the UV luminosity. The other one is ultraviolet slope. So what you do is you fit a power law in this range from 1500 to 2600 angstrom, and the power law index is called UV slope because in log-log plot it is a straight line. And these two actually fit the normalization and shape of the spectra. And when you observe a lot of galaxy, you can study their distribution. The distribution of UV luminosity is studied using something called luminosity function, where you just bin various observed luminosity in different brightness bins and normalize it to volume, and that is the luminosity function. And UV slope, you can study the scatter plot or something. Okay, so like for past decade, what people have been doing, so they have running simulations and they have calibrated the UV luminosity function in the present like local universe redshift around 0. There are also semi-analytic models, and also people have like the observed luminosity function, they have calibrated it how it evolves with redshift. Now when they extrapolate it to very high redshift, it doesn't work. That's what the initial early results suggested, as you have seen here 2022. And now we also have like spectroscopic confirmation, and we see still that there is some not like the data is not agreeing. So this is the typical situation. You have observational point and theoretical prediction, and they are not matching. So, and people have been addressing this from all directions. Observationally, what they are doing, we want to reduce this error. So to account for the cosmic variance, you can look for various direction and do large volume survey. You can do spectroscopic confirmation and reduce the contamination, and accurate photometric data reduction. And for some sources, this is actually helpful, like they do come this side. On the other side, you can like theoretical side from cosmology and galaxy formation, and at high redshift they are actually related. From cosmological side, you want to push this upward by forming more number of galaxies, and you can do it this with blue tilted power spectrums and non-Gaussianity. I'll not talk about that. What we are interested in is galaxy formation. So push this curve this way, that is to form more brighter galaxies, and reality might be something in between, we don't know. But in the galaxy formation, there are a lot of uncertainties, and like since the beginning people are suggesting various this analytic model, and they have explored these models, how it is helping this like this thing. But all of these effects are very much coupled in galaxy formation. And to correctly account for this coupling, simulations are very powerful. They account for all the nonlinear physics and coupling between them. And but these simulations are very expensive. If you run it to redshift 0, it takes about 6 months or something. But we have an advantage because we are analyzing our data at high redshift. We only need to simulate for 1 billion year compared to 13 billion years. So that is 10 times less time. So we can play with more parameters and check more things. So we do simulations. So this is an overview of how these simulations are set up. You start with a homogeneous distribution of particles, dark matter and baryons, and then at your starting redshift, your initial conditions, your starting redshift, you generate a power spectrum using Boltzmann called class, and then you offset this particle, this small perturbation, from linear theory. It gives small position offset and sets the velocity of the particle consistent with the power spectrum. And once your IC is generated, the gravity is standard n-body code, and for the gas particle we have all these cooling physics included in our code in SPH formalism. As a result of that, this gas particle, it condenses into the central region and its density increases. And at certain point, the ISM is like when the density is increased enough, the ISM is treated with subgrid manner. And after certain point, when the over density of our gas particle crosses some threshold density, we switch on the star formation for our baryon particles. The stars are formed stochastically in a probabilistic manner over multiple generations, and when stars are formed, they give supernova wind feedback to its neighboring particle, wind feedback and stellar feedback like hitting them, and the metal return. We also have black hole formation criteria and the related feedback in our simulations, but I'll not talk about the black hole because they are not very effective, at least the model we have till now, they are not very effective at high redshift in terms of that they have not accreted enough mass, so the feedback is not enough there. So this is okay. So we have run this hydrodynamic simulations with the code called MPGadget. It's publicly available with Planck 18 cosmology, and here you see how all these blue points. Okay, we call our simulations Ninja by the way. These top 3 points, these are run at IUCAA, and all these bottom points they are run at NISER Bhubaneswar. And this is how it compares it like very popular other simulations. They are all aimed at a different goal. Some are like with little bit older cosmology. Older cosmology, and our model closely matches with this Astrid simulation, which is sitting there. The best resolution we have is for the baryon mass. We have is 2 times 10 to the 5 solar mass, which is sitting here. So this side is best resolution. That will resolve your subgrid physics better. But you see, this resolution is like comparable or even better than like Millennium TNG, but they have 10 times more volume, which is needed to probe those very large, massive galaxies. But because of limited computational resource, what we do is we run multiple boxes, and we stitch like different boxes probe different mass range, and there are techniques to stitch these boxes and probe a larger dynamic range, which is what we do. And this is one of the picture we have for this 50 MPC 1008 cube particle at redshift 0.5. You can see the dark matter field, gas field, stars field. Black holes I have not shown, zoomed in picture here. However, just because at low redshift the structures are more visible. However, my analysis today will present that will be for above redshift 7. Yeah, so before going to light generation, we want to make sure that our structure formation is okay. So here we see the something called dark matter halo mass function. This is just similar to luminosity function, where instead of counting the brightness in various bins, you count the mass in various bins. And we see that for various resolution of our boxes, they are on top of each other, which is a good thing because you want to make sure your results doesn't depend on your resolution. This is good for dark matter. Also for the gas particle, that is also pretty much well conversed. But for star and gas metal mass, you see small deviation, which is coming because of the resolution effect. And then there are techniques. Yeah, so here I have shown the dark matter mass to stellar mass relation, and you can see that they are not a perfect straight line, although there is a linear correlation because of this resolution effect. They are not matching. And then there are techniques to correct for this mismatch between resolution, and when we correct, we see that the agreement is better. It's subtle, but it's there. And here we have shown the other two plots which are relevant for my talk. One is galactic main sequence, that is the correlation between stellar mass and star formation rate. And we see that like one of the observation is going through all of our points. This edges you see because of various boxes we have put here and some cut we have put here. There is gas metal mass to stellar mass correlation, which you see is a very well defined correlation that is present on a simulation, which will be relevant for my talk in some later slides. Yeah, now we want to generate light from these things if we want to compare with observation. So first thing is the intrinsic and nebular light. So what we do is we take BPAS spectrum. I'll just explain it briefly our light generation. So we have templates from BPAS, which actually takes into account the binary fraction in galaxies. That's the standard what people are using nowadays. And all these templates, they have very much flexibility in terms of they give us like 9 IMFs, various S beams, 13 metallicity beams from primordial to 2 times solar, and spectral cover is very good. And we pass these templates to cloudy photoionization code and get the templates for like nebular emission. And here what I have shown, so if you see the mass resolution we have, it is like 10 to the power 6 solar mass, or 10 to the power 5 solar mass for the best we have. So when you say one star particle in a simulation, physically it is actually a star cluster. So the light one single star particle generates in our simulation, that is actually something called single stellar population, where all the stars are of same age. And what BPAS provides us is the same SSP synthesis. And here I have seen one of the example of the intrinsic light and the template from the cloudy photoionization code. You see the effect of including the nebular emission is to change the slope a little bit. It will affect our result. And yeah, so that is for one single star, but our galaxy has lot of stars. We'll see like 10,000, 30,000 stars. So what we do is for all of our stars carry their age, metallicity, and mass. So based on those information, we pick the appropriate templates and we add them. We correctly scale for the mass because BPAS provides us for 10 to the 6 solar mass. Yeah, so that is how we generate the intrinsic light. But we know that a little bit of dust will affect a lot, a lot to the light, and modeling dust is difficult. That's why everybody does it differently. What we did is we start with a simple scaling law, where people observe the visual extinction. Visual extinction is the intrinsic light and the dust suppressed light. The difference between them in the visual band, you call that the visual extinction, V band. And there are different techniques. People observe visual extinction and total hydrogen column density, not the neutral one, total hydrogen column density. And they find a correlation between those two quantities, and you also expect it from the theoretical grounds. And these are, by the way, points from the Milky Way galaxy with supernova remnants, planetary nebulas, X-ray binaries. But when we apply it to all the other galaxies, we have to account for the metallicity, different galaxies have, which is scaled with a power law here. And so this term, this relation between visual like V2 and H, that is there, we scale for the power law, and these two terms becomes the metal column. And then we apply a first factor. The kappa is this factor which is coming from here. Then we account for a first factor to account for the variations at the like cosmic down early universe case. Yeah, so here you see that if we can find the metal column density, we will directly tell the AV and we can then use it. So, and finding metal column density is straightforward. From every star we shoot a sight line, and at various points we probe the nearby gas particle, gather the SPH contribution, that will give us the metal column density at a single point, and then we just integrate it, that will give us the total column density for a star. Okay, so so I'll go first then. So that is the straightforward, but what we have, we can either shoot sight line from the central, like every galaxy is a central star, that the potential minimum, we can find the intrinsic light and apply one single attenuation load to the whole galaxy, that is called central attenuation, or we can shoot the sight line from every star particle, that is actually more accurate, and we see that this every star particle shooting, that gives us visual attenuation which is more close to the observation. And this is so this is what we are doing. We are independently modeling the SED, which we plan to then. So we want to mimic the observers. We will feed it to the SED recovery, so like backpipes, for example, which feed the SED. We can pass there because our generation is independent. We can check if like different SED software, they assume different star formation history, so whether that has any effect on our relation. We can also, because we are generating the column density, we can also find the neutral hydrogen column density, and we can generate the DLA here, as you have seen here. We generate bandpass photometry at various ZWST bands. We can generate image, the pixel image with ZWST. We add the noise given from the ZWST sensitivity. we convolve with the PSF, and because we didn't run any hello finder, we use source extractor to find the sources, and if there are various hellos linked by a filament, we will find it there. So now I will directly go to the results. Here what I have shown is the luminosity function at redshift 7, and we see that it goes through all the the agreement is good, and here it is missing 2 points. First of all, this side some of them are Asian contaminated, and above this range they are mostly Asian, and here you can see the difference between the intrinsic light and the dust attenuated side, the importance of dust. And this faint tint side, you see that they are not affected by dust, which is also shown here. So you see this is the relation between intrinsic and attenuated magnitude. You see that at faint end there is basically no effect of dust. At high end there is a upturn, which is seen in our data, and this is also seen at blue tides, which is actually like precursor to asteroid, our closest model. And this happens because when you have more bright galaxy that is coming from more star will also result more metal mass, which will produce more dust and hence more dust attenuation. And because this faint, so yeah, you see this side, because of this large AV, they will their column density is more than 21 centimeter square. They will totally block this neutral hydrogen, totally block the UV ionizing photon. So what we see is that our models show that the reionization is mostly driven by the faint end galaxies. This luminosity, yeah, it is not changed. This model is for Savrier IMF with epsilon 3. These are what we have taken. I'll see what happens when you change this thing. Here what we have done is, so there is different attenuation laws people use. Three of the most cited ones at high redshift are Kalgiti for starburst galaxies, Gordon, which is standard for low metallicity galaxies, and something which people inform from supernova, because they say that high redshift stars don't have enough time, dust doesn't have like this AGB star dust formation channel, the stars doesn't have enough time to go off from the main sequence. So this is mostly informed from supernova, and the law is basically what this attenuation law, it takes from AV to AUV, and different attenuation law will give you different suppression and also change the slope. What we saw is that different attenuation law does change here. We can see two lines because two of them match here, so one is on behind of another. And in the bright end we see that this is suppressed as shown from here, but this can again fixed with this epsilon. But in the faint end side we see that there is no effect from the dust model. We can also see there is the epsilon here. So what is epsilon? Is it the first factor? And so this basically goes, different epsilon basically relates to different grain size distribution and different composition. And we see that it is between 2 to 3. We have not done chi-square fitting or maximum likelihood now, which we plan to do very soon. And we can see that all of them still go through the faint end, but bright end, but not the faint end. So this end actually can be useful to, this is not affected by dust, so this can be used to probe IMF effect and effect of star formation efficiency. Here we have shown for the IMF. So IMF basically gives you the distribution of various stellar mass in the mass range in a cluster. We can discuss this later since I have less time. And we see that top heavy IMF, which has more massive star that produces a little bit bright light compared to bottom heavy. And this faint end side is now affected. It is a little bit good, but still it's not passing through this thing. So this results can be used to constrain the IMF effect. But brighter end there is still degeneracy. Yeah, I'll just stop up. So this is our result at various other redshift. This is showing the star. So the effect of different star formation efficiencies. So we have some model to enhance star formation efficiency with weak wind. We can explain it later. You can see it is there, and different morphology coming from different models. This is the same galaxy. This is how constant dark matter mass to light ratio and other results basically compared to our light synthesis model. And one other thing is the UV slope, which we are still doing this thing. This is so this is the UV slope and how it's compared to observation for various attenuation law. And as I said, in the bright end there are lots of degeneracy. So this will be like you see Kalgiti and SMC, one is going top, one is going through. So this will be helpful to break that degeneracy. As you can see here, one of the curve is going better through the observation, and our future work we can tell about this thing.
Thank you. We can have maybe one question.
Yes.
Okay, very good.
Hi, Ranjit. Very nice talk. Couple of questions. I have only one question to ask, so I'll list them now. So I'll wrap it up. How do you model the star formation rate evolution with redshift? And given the fact that the supernova feedback will depend upon the stellar mass, so depending on the change in the IMF, how do you regulate the supernova rate?
Yeah.
But there are
So-
more questions here lastly.
Yeah, I missed this because of time limits. So one thing is, how do you model the star formation density? That is self-consistently modeled in the simulation from all the feedback. Second thing is the effect of IMF on star formation rate density. That is not modeled in the simulation now. So that improvement is needed from the simulation side. Only the metal return in the simulation depends on the IMF, which is actually takes the Savrier 300 IMF. It does also depend, which is not modeled there. So those improvements are needed from that side.
One more question. Okay, Ranjan.
Hi, Ranjit, thanks for the very nice talk. I have a question. In your simulations, do you resolve individual galaxies? Because JWST has measurements of the stellar radius.
Yeah, you can see, right?
Half-light radius, right?
So I have one picture actually. Yeah, so here you can, this is one of our galaxy.
So does your half-light radius match with what, say the JWST measures? They suffer
So, yeah,
these
this is
rates
one of
7
our
a day.
plan. In our future work, we'll measure the morphology distribution.
Okay.
And this will affect from various models,
Yes,
which
yes,
we
yes.
also plan to run in the future. So this is one of our future work to run various models, morphology study, calibration. These are one of our study which we will do.
Okay. Okay. Thank you very much. Thanks.
Yeah, but the radius is in the ballpark is correct now, but lots of calibration needs to be done because the software we want to exactly mimic the observers, want to run the source extractor, Galfit with observers too, and they have a lots of parameters, those software themselves, so a little bit calibration is needed. Yeah.